Now moving on, we will now discuss the mixed average file. An overview of the mixed average file. Again, this file provides the key flow parameters at the upstream and downstream locations. But instead of the mean line or mass average values, this file outputs the radial profiles or 2D profiles at these two stations. And this allows the user to compare the output with streamline type of calculations that very likely they had done earlier in the design cycle. Now, prior to these profile tables, there is one table that's provided that provides some feedback on the parameters associated with the execution of the computation. And this table is shown here. Very briefly, it shows that the case title, the number of iterations that were executed, in this case 6,000 iterations, and the sector that the output is relating to, the turbulence model that was used, the grid that was used. Then it goes to give some information on the inlet, the max Mach numbers, temperatures, pressures, some reference density and velocities that are used in the calculation. And this is really getting into the more details of the computation. And then more importantly, it gives the inlet Reynolds numbers, the surface roughness that was used, the turbulence level of the mainstream flow, the length scale, the molecular Prandtl number, the turbulent Prandtl number, and any heat flux boundary conditions that might have been imposed. And it also plays back the number of airfoils that were for this particular row. This information helps the user kind of double check his input and what was used for the calculation. So it's kind of a sanity check. Now, with regard to the radial profiles, the radial profiles really key off of the meshing for the particular case, which for the radial direction or the span-wise direction are the K planes. And for typical calculations, there are 40 to 50 radial mesh points used. And so those are the radial points that are output by the code for the radial profiles. The next chart here shows the meshing for a blade row. It happens to be the blade for this research turbine. And there were 41 radial locations used for this computation. So highlighted there are one of the pitchwise strips that are used, and there would be then 41 of these strips. For each one of these strips, the flow would be mixed out. Remember, the flow is varying in the pitchwise direction. It's certainly not uniform. This is a 3D computation. So this flow is mixed out, and it's this mixed out set of conditions, pressures, temperatures, that are reported for this particular radial location. And so the next chart here provides a typical or example table. This is for this research turbine, and this table is for the upstream of the blade row. So we were looking at the front of this mesh, and so now at that upstream location, this is the radial profile, or the pitch averaged radial profile for this computation. And so across the top in the blue, you can see are the particular parameters that are provided. And I'm going to go through it very quickly. The first columns are the velocities in the orthogonal directions. Next would be the relative Mach number, the percent span, the absolute Mach number, absolute temperatures, pressures, the air angle, meridional air angle in the absolute and relative frames, the pitch angle, phi, the static pressure, the axial location, x, physical location, and the radial location. Now, I've gone through this very quickly, but the user can go to the user manual. It gives a detailed explanation for each of the parameters. And again, if there is any kind of question, please feel free to contact ADS, and we'd be very glad to answer your questions. The next chart here is just an example of plotting one of the parameters. And what has been plotted here is the relative gas angle going into the blade. And you can see the dots on the blue plot are the individual points. And you might notice that at the end walls you see kind of a very funny, abrupt swing in air angles. And what you're seeing there is the end wall secondary flows at the root and tip of the passage. And these flows, vortex-like flows, have very strong angle changes, and it's very well documented in the turbine literature. Also shown is a red line, which is called the design intent angle profile, which is a streamline angle profile, and this particular streamline doesn't recognize the strong secondary flows. Okay, but you can see that in the midspan, most of the region of the airfoil, the computation, the 3D CFD computation, and the design intent are pretty close in agreement. So the designer at this point would find that his design is probably going to be acceptable in terms of overall flow. But again, this information that's output allows the designer to do these type of comparisons. They can be automated. Scripts can be written to automate this and to do it very quickly. In addition, the mixed average file provides information that goes and beyond the 1D through flow information. For one, it integrates the radial profiles to give 1D through flow calculations, and this is totally consistent with the dot mean value output that was previously discussed. But it also provides additional information that is based on a full span-wise integration and includes torques and axial forces, which are very important in the early stages for doing structural analyses, bearing sizing, shaft sizing. So the next chart here provides this output table. I'm not going to go over the first line. That is pretty much has been covered before and is almost very self-explanatory. But line 2 starts off with the flows. We've covered that before, but then moves on to the axial component of force on the airfoil, and this can be used to size attachments and forces on the airfoil due to shear, and there may be some reasons that the designer may be interested in that. Those are typically relatively small. The pressure forces are the dominant forces typically. Next are torque forces on the airfoils. Could be used to size the attachment fasteners or shaft torque reasons, sizing the shaft. And then due to airfoil shear, again, the shear forces are a small force on it, but because this is a full 3D calculation, we're able to get that level of detail. And the radial forces on the airfoil due to surface pressure. And typically these forces are small and are not picked up in component calculations of mean line and streamline, but because of the detail of 3D CFD are picked up. And again, radial component of forces on the airfoil. And all these definitions are provided in the user manual. This next term is the power extracted from the airfoil row. This is the net force, pressure, and shear forces transmitted to the structure. Net torque transmitted to the structure, and the net radial force. This information provides the designer with very detailed information to execute airfoil preliminary structural analyses. And then later files can be output which would allow the structures people to go and basically paste on these forces into any structural code for very, very detailed calculations.